The second question is only a question 4 from this particular paper. So if you consider the last one was a question 6, so considered to be much easier. I'll put this one second, however, because it is a show that, so rather than just working out the speed, it's asking us to show that expression. But considering the marks, considering where it is on the paper, it is an easier situation. So we've got a hollow cylinder. You've got a particle being projected inside this hollow cylinder, and of course you know just from experience, you project that up, you kind of throw it with velocity, it will stick to the side of the cylinder, but at some point it will fall off. It will fall off, and that is because it's the normal reaction force that, of course, is keeping that on the surface of the cylinder. So the second part is all about that situation when it does leave the cylinder, but for the first part, we just need to think about how we can work out that equation. It's exactly the same as we've been doing. It's all about using energies in the first instance and then looking at resolving the forces. So I'm going to call that point A, I'm going to call that point B. Write down what we know at each of these parts. I have got an angle here of theta, and I know that the length this time is, or the radius rather, is 0.6. So I'll write my 0.6 there. So at A, I'm going to consider A to be my 0 level, so h is equal to 0, and I know my velocity is equal to 4. Total energy, write down what you're doing. GPE plus KE is equal to mg multiplied by 0 plus a half m multiplied by 4 squared. That, of course, is 0, and that just gives me with a half of 16m, which is 8m. So now at B, we've got to work a little bit harder here, particularly considering that height. So I have got all of that 0.6, but considering this triangle here, I need to subtract that little bit there. Let's do that in a different colour. Subtracting that little green part there. So if you think about this triangle here, if you want, draw it out. This is my triangle there. I know that is 0.6. That is my right angle. That is my theta. I have got the adjacent side. Of course, you can tell exactly the same from there. If your original diagram is big enough, of course, so that's one reason why drawing a big diagram is better than little ones that some of you sometimes draw. So it's the cosine component. So I've got 0.6 minus that green part, which is the cosine component, so minus 0.6 cos theta. So now I can work out my total energy at B. It is mg multiplied by h, which is that 0.6 minus 0.6 cos theta plus a half m v squared. So what we do now is we equate those. Conservation of energy, 8m is equal to mg 0.6 minus 0.6 cos theta plus a half mv squared. I again have all my m's cancelling. You always know they're going to cancel, but you must make sure you put them in at the start, otherwise that's just not correct. So you can't just think, right, I'm going to cancel it at the start. It only cancels when you equate the two energy equations. So if you look at what we've got to prove, v squared cos theta, that's what we have. We've got a v squared and we've got a cos theta. So this is now just about sorting that out to get to this expression. Just be careful though, because it is a show that. So don't do too many steps at once, even if you think it's perfectly fine, because it's a show that. You have to just take a little bit of care and maybe do more stages than you would normally. I'm not going to pick up the calculator yet. I'm going to multiply by that. I'm going to multiply by 2. minus 1.6 g cos theta plus v squared. I want to make v squared the subject. So I've got the 16, I am subtracting 1.2g, and I would be adding that 1.2g cos theta. 16 minus 1.2g, so I'd go to the calculator now. If I work that out, I've got 4.24. 1.2 times that times g is 11.76. Okay, so there we go. Same as we did before. I guess that's maybe the most awkward thing, finding that length, but everything else there is pretty standard. So for the second part, look, 4 marks. So they're thinking that this is much more straightforward. Another diagram. Another diagram, because I'm now focused on what's going on here. And of course, we've got to be really careful about our forces. We're resolving towards the centre. So on the particle at any one given time, I've just written down what those forces are. I've got the mass, or the weight rather, and I've got the normal reaction. Even though we know that that is going to be 0, I'm still doing the general case, and I'm marking that on there. That is acting towards the centre. If I continue this line down, then I know that that angle there between the weight and the line towards the centre is the same as theta. So of course we've got a corresponding angle there. So I can mark on that theta. Resolving towards the centre and using F equals ma. Forces going towards the centre would be R. And of course the mg, if you consider this triangle here, the component that we want, this one here, is acting away. So it's acting in the opposite direction to R. So R is heading towards the centre, away from the centre is the weight component. Again, some of you might want to draw this triangle out here, but it is my angles there. I want that component, it's the cosine component. mg is my hypotenuse. So it's going to be mg, mg cos theta. So r minus mg cos theta is equal to ma. So m, we're going to use v squared over r. But of course we know that when it leaves the surface, that is the point at which there is no contact, so r is equal to 0. You could, of course, just write that at the start, but I think it's nice to actually physically see that force in the diagram. That, of course, is still true. It's true at any point, but now we're looking, or I'm looking at this particular point here. mv squared over r, and I think we know r, don't we? Yeah, that's the 0.6. The m's cancel. And I have got g cos theta equals v squared over 0.6. So if I make cos theta the subject, I've got v squared over 0.6 divide by the g, the negative g. And the reason that I put in that form is that now we can look back at part 1. Here we had an equation for v, and in particular we had a cos theta expression here. What I've got is an expression for cos theta. This is the angle, however, this is the cos theta for which the r is equal to 0. But I can substitute that into there. So it means that we would have, if we substitute, v squared is equal to the 4.24 plus 11.76 multiplied by this expression here, minus v squared over 0.6g. V squared is 4.24, and if you work out 11.76 over 0.6g, you get 2. So the question obviously has worked out its numbers. really carefully. We then, of course, have got that minus 2v squared. Pop that over there. 3v squared rather is 4.24. So v squared is 4.24 over 3. Square root. And we have our velocity, which is 1.19 meters per second. Okay, so that seemed an awful lot less than the previous example, even though that first part was algebraic. It's exactly the same methods. Okay, don't worry at all if that first thing you have to prove is algebraic. It's just a bog standard energy expression.